Now, of course, it's not always a very beautiful story. So, if this was the best algorithm, I would have very jubilantly said that, hey, we've solved a great problem. Now let's discuss it a little bit deeper, and let me give you a little bit more intuitive insights, maybe, of what happens. Now, previously, I spoke about two behavior, obstacle avoidance and goal seeking. And I said different times the two behaviors will interact each other and some kind of an equilibrium has to be established. In agents and in robotics, it's known over here. So I take a simple scenario. I say my robot starts over here, or that's the source, and my robot ends over here, or that's the goal. Now, that's how the robot goes, potential field, and this is called as the path length, and this is called as the clearance. And the two objectives are completely contradictory to each other. Let me show it by an example. So, the same scenario twice. So, this one has a large clearance and large path length. And this one has a small clearance and small path length. Generally, I need to maximize clearance because what happens in small clearance, the robot can make some errors and collide. All the sensors are noisy, so we don't even know where the obstacle is. We just have an indicative idea of the obstacle. We don't even know where the real obstacle is. So to be safe, I want as clearance as possible, which is in a modern world, you call it as personal space. Nobody comes here, nobody comes here. My personal space. So when somebody comes too close, you get conscious. God knows what will the guy do. You don't have that much of trust unless you are close friends. So, larger clearance is always better for robotics, and smaller path length is always better in robots. So, it's a trade-off. It's good by clearance, bad by path length. It's good by path length, bad by clearance. Now, what's the trade-off between the two behaviors, obstacle avoidance and goal seeking over here? If I increase the attraction force, the attraction is so nice, it's so large that the robot goes running. It doesn't much care about the obstacle. So attraction is too large. It's feeling the repulsion, but the attraction is smaller. It's feeling the repulsion, attraction is smaller now. Two charges can never touch each other. I mean, two same charges will have to repel. So if once it goes very close, the repulsion becomes almost infinity, 1 upon d, and d is so small, cube. Then it starts to repelling. So the clearance reduces and the path length reduces. So out of which this is bad and this is good. Clearance and path length are opposite to each other. If I increase the repulsion force, so I put more negatively charged particles. I put too many negatively charged particles. So now what will happen is a robot here only will start feeling repulsion. Attraction is small in contrast to repulsion. It will start feeling the force. So clearance increases, which is good, and path length increases, which is bad. And therefore, multiple robots will have multiple constants which will enable them take multiple kind of distances. Some will go close to the obstacles, some will go far from the obstacles. And how much distance do the robots in general keep from the obstacle, it is governed primarily by the constants that derive it, the attraction and repulsion constants. Now, a very frequent thing that people, of course, in simulation classes say, and I have also said that, there's a guarantee. There's a guarantee that two negative charges will never collide. And the guarantee is given by suppose Q is towards collision with obstacle O. That means dq comma O, it tends to 0. That means if repulsion at Q due to O, it tends to 1 upon d cube, which tends to infinity. So that means as your robot comes very close to the obstacle, it feels a near infinite repulsion and it can never collide. It can never collide. So theoretically it can never collide. If you are from a physics background, the magnitude of energy that will be required to fuse two electrons together is infinity. And you can never do that. Practically you can never do that. But then if you implement the potential field, which you will have to in your simulations, which we do next, you will see them collide, and many people are like, what just happened? We proved physics wrong. You actually did not prove physics wrong. Let's take an example. All of us are doing what is called as a discrete simulation. A discrete simulation means that you have at time t, you decide the control input and implement to get the state or the pose at time t plus 1. So that's what we say. And this is what is the kinematics of the system. In other words, what really happens is, in a general sense, this is the kinematics equation that says to a robot at a position or state qt, I apply a control input, which is linear and angular speed ut for delta t amount of time. So that's what happens. I get a new state, I get a new pose. Wonderful. And then I apply for another delta t, I get at t plus 2 delta t, and so on and so forth. Where this is the frequency of control. So typically you will operate them at, say, what? Once in every 100 milliseconds, once at every 500 milliseconds. If you operate once at every 500 milliseconds, what happens is for 500 milliseconds you don't have any control. That means for delta t times, I have no control. And the robot moves by the same old ut. Now coming up to the example, so let's say the goal was here, the robot was here, it's far away, it barely felt any repulsion. It moved for delta t times, it's again far away, it barely felt any repulsion. It moved delta t amount of time, now suddenly it's almost colliding. So the problem is when from here to here in this delta t amount of time, the force went from near zero to near infinity. So I applied the control over here, but the problem was that the second control that I got was over here. That's one problem. The second problem is that the robots have kinematics. You cannot go at 100 km/h with your vehicle and suddenly get into a zero speed. You've got kinematic constraints. The robots have those constraints. You cannot suddenly stop. So even though you applied maximum brake over here, you were traveling at 100 km/h and you just couldn't speed down. So the problem is that it's a discrete simulation, and for delta t amount of times you don't have any control, and that is the same example that we give for human driving as well. Why not drink and drive? Your reaction time is delta t. For delta t, you are not doing anything. You look at something, it takes delta t amount of time to process. Till that amount of time, you're going by the same speed. So if you drink and drive, you say the vehicle is far away, let me continue at the same speed. You look at the vehicle close by, for delta t amount of time, your processor is processing. By the time you act and tell your legs to apply the brake, the accident has happened. If it was a continuous system, vehicles can never collide, which is why people don't collide when not drunk, continuous, attentive, because then you're operating at a few milliseconds. Delta t is just a few milliseconds. So if you see potential field robots colliding, it is not because theory is proven wrong. Theoretically, robots can never collide. It's because of the discretization that is applied and the kinematic constraints, of course. Now, let me take in all this is good. Now, let me give away with the simulation thing and go a little bit towards the practicality. Is this the best algorithm still? And the answer is no. The first problem with potential field is that it gets the robot stuck. And let's take a very simple scenario and let's simulate it up. That's a ball. By the way, it's a practical scenario. When we executed physical real robots with the potential field, that was one of the first things we learned. That's your robot. That's a goal. The robot comes over here, attraction, 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 repulsion, attraction, repulsion, attraction, repulsion. So let's see what's happening around over here. By a free body diagram, there's a attraction towards the goal, and there is a repulsion from the obstacle. The two forces are equal and opposite, and this is where the F total is equal to 0. And this region is called as the equipotential region. It's also called as a local minima. We took examples of rivers flowing, water flowing. All of them are local minima. What are lakes? Rivers flows from the mountains, gets stuck at a local minima. That's equipotential. So practically an environment will have many such local minima. In the previous example, if I actually start pointing out square obstacles, there were many local minimas. So in a local minima, in an equipotential region, the total potential value is 0, not because it's a goal, but because of the fact that it's local optima. The forces cancel each other out. There's another example because we're dealing with multiple agents. So that's the other example. I've got 3 robots. Robot 1, which wants to go over here. So it has a towards its goal. However, there are also two other robots, and they want to go here and this wants to go here. So if you draw the free-body diagram of this, repulsion due to 1 and F repulsion due to 2. Now, it turns out there's a little thing that is again nature inspired and pretty intuitive. So when it rains, water also gets logged in right behind me in the road, but that doesn't stay long. So what happens in nature, sometimes when you apply a perturbation, the local minima problem is solved. So water gets stuck in, you just shake it a little bit. And once you shake it a little bit, it vanishes. So and that's exactly what will happen over here. So I'm here, the other two robots are here. I'll shake this a little bit, I'll shake this a little bit, I'll shake this a little bit. They'll again get stuck around over here. I'll shake it more, I'll shake it more, I'll shake it more. Eventually a situation will come when shaking the three robots is going to happen, and now it's no longer an equipotential. So the equipotential region can be broken just by shaking. So I apply a new force which is called, when robot is stuck, what I do is I apply a new force which is F rand, which is just random, and I keep on increasing its magnitude along with time. Now if you just apply it random, you keep on applying it at a different place. So what you do is you select a random direction and you actually keep on applying it a little biased towards the random direction. And you keep on increasing the force and you keep on increasing the force and you keep on increasing the force. So you're stuck, you've detected it, you're not moving. You say, let me apply to the whole system a little bit of a random force. So you apply a random force and just wait for it. Most of the times the system will get back to the same state, same equilibrium again. You apply a little bit more of force and then you wait. And then you see it sometimes gets stuck at the same minima again. Then you apply more force and then you wait. It gets back in the same position. You apply more force, it gets back into the same position. Once upon a time, large enough force, you apply a lot of force, random direction, just keep moving a little bit biased towards that random direction for a longer time. What happens now is that the local minima gets resolved. That's exactly what will happen over here. So I'll apply a little bit of a random force, it'll again get stuck. I'll apply another random force, it'll again get stuck. I'll apply another random force, it'll again get stuck. I'll apply another random force, it'll get stuck. Eventually I'll apply some random force and it'll get out like this. Now the problem is that theoretically speaking, every minima can be resolved by applying sufficient quality random force, but then after doing that, what you do, you go out of one minima, you go into another minima, then you go into the third minima. So you can, in your entire life, keep on switching minima, and that is not a practical solution. So the actual solution is not a part of this course where we fuse the A-star like global planning algorithm with the potential field algorithm. Like, remember what I said about the corridor thing. If you would have known that this is a topology, you would have applied attraction force not towards the goal but at the corridor end, and you would have been out. So that's one of the major problem with the potential field. There's a little interesting problem as well. That's at narrow corridors. And if you had a class on control theories, you will understand exactly what this problem is. I start from here. I primarily, that's my goal. I primarily feel repulsion due to this. I go here. Here it's equipotential and the attraction and force cancel each other out. At this line, attraction and forces cancel each other out. But remember, a robot cannot be at this point of time, at this orientation, suddenly be made to oriented in the direction of the goal. It's kinematically not possible. I allow you to have an erroneous control by saying whichever way you control force into immediate velocity, that's okay for the current simulations, but practically the robot cannot suddenly turn. So it'll continue to move here. Of course, it'll slowly and slowly turn, but that's how it goes. Now it feels attraction over here and it comes around over here, and of course it will not stop here because of momentum, because of kinematic constraints. It will continue over here. So narrow corridor, that's actual motion. It's called as oscillations. And you would know it, P controller, what happens, oscillations. Here we still don't have a PID. Attraction to goal and repulsion from the obstacles are more or less saying that as error increases, the magnitude by which they force the robot, it reduces, but there's nothing like the I and the D part of a PID controller. So it'll continue to show in these kinds of oscillations, and because it shows in these oscillations, it's actually pretty bad.